Hello, and welcome to the introduction talk on open instruments for reproducible data science and industry. My name is Anna Dubovic, and I will guide you through the current oil and gas industry situation and technological breakthrough that we have achieved recently and open it to the public. It has been stated before that the nature of oil collectors has changed and that software, which served the needs of oil sector faithfully, are no longer suitable, since the oil is much harder to locate, estimate, and extract. Nowadays, deep learning algorithms have delivered extreme value in almost every sphere of life, and of course, all vendors started attempts to tame its power. At an early stage in the oil industry pipeline, the cost of mistake has extreme influence on the project. It influences collector estimation, exploratory drilling, and every step that follows. As it has been stated before by Nvidia and Equinor researchers and many more, human interpretations are visions with educated guesses, and along that are time-consuming and subjective. At the same time, the market of quality data science brains is extremely limited, even though every computer science graduate calls himself a senior TS developer. We all know that's not true. This means that for each one proper data scientist invested, best returns will be in the upstream sector. I believe all people in industry are still in doubt. Is it actually worth it? Well, we went all the way through, and here's what we bring to the table. Just one deep learning model can outperform experts in time, quality, and resolutions. Due to project time constraints, software limitations, and most of all, human factors, experts can neglect whole formations. You can see that in the bottom left. And miss crucial details that might mislead your oil collector's crusade and leave you with empty pockets. Model performance on the right has complete coverage, and even though it's not 100% fantastic, you get a complete picture in the matter of hours. Not to mention that the horizon coverage area on the real-life field is exceeding 2,500 square kilometers. Also, models can be supplied with attention mechanisms, which will help the model understand itself and grade its work. Humans tend to be human in this task, and you want brutal honesty. In exactly the same way as previous task on horizon peaking, we have deconstructed upstream pipeline on stages that can be converted into deep learning solutions. They all are based on the same technology, which we also published on GitHub, so you can make your process of applying AI in production as automated as you want. You can create single-stage models or make them transfer data from one to another. All libraries use the same notation, so data flow goes seamlessly. Many service companies are offering their customers all-in-one solutions that they swear that the more complex and gigantic the software is, the more power it has. But that's not true. For each stage in upstream, we have assembled a dedicated library with everything ready to use, pre-processing, models, metrics, monitoring, and all you want. I'll go through each one to give you a taste of what can be achieved in a matter of days with this toolbox. Core library for all our stack is Batchflow. It sets format, approach, and notation to everything we deliver in the world. We aim to compete with the best and most common solutions. And for now, Batchflow has every necessary segment to help you build production-ready code. Of course, you can always write your own model from scratch. But why bother if you can snap it from the Batchflow collection? We have published extensive documentation to all our tools, and to start using them, you don't have to hire a department. In collaboration with EEG community, we have just finished leading series of educational workshops where geoscience experts, without any prior knowledge, have been able to achieve production quality in 4-hour course. Configuring sophisticated neural networks with just a few lines of code. We've written our custom wrappers for TensorFlow and PyTorch, which allows us to use short configs to define even the most complex architectures. Our model Zoo has a huge number of pre-implemented architectures, ranging from plain old UNet to Deep Lab v3 with all the modern bells and whistles. If you don't like any of them, It's easy to build your own model from predefined blocks like ResNet block, ASPP, exception block, and whatever. We can't process large batches of seismic data because of their size, so we have to reduce batch size. Unfortunately, gradient descent becomes less stable. Microbatching helps us to compute gradients for the large batch by splitting it into few microbatches and accumulating gradients. Batch flow enables that by one line of code. Moreover, we can process batches in parallel using multiple GPUs to speed up model training. Today, that option is incredibly important due to the availability of clusters with GPUs and necessity of their effective utilization. Multi-GPU training also can be enabled by only one line of code. And again, all unified, structured, described in papers, full mode supported by our team stack, and we're currently extending. If you join us on this route, we can smash industry by the end of this year. Now, I'll bring examples of ready-to-use models where you just need to insert your data and get results. Yeah, we're working on data release as well. But for now, you have to bring yours. Otherwise, we would be taking all the fun out. And that's unfair. Seismic Pro is a framework for machine learning on field seismic data. It provides tools to load, process pre-stack seismic data, and use it to train machine learning algorithms. Seismic Pro supports data manipulation and visualization in different representations, such as raw seismic traces, common shot gathers, common midpoint gathers, and etc. This allows us to conveniently apply various processing actions and to employ different approaches to train neural networks. By now, the repository contains ready-to-use models for ground roll noise attenuation and first break picking. But most importantly, we have a dedicated model called research that ensures that we have not only taken a random model and received a random success. Reproducibility is key. Exploring hyperparameter space by running a number of experiments simultaneously. With all the wealth of parameters that is presented by our framework, we need to make a lot of experiments to narrow the exact architecture down. To this end, we have a special model that runs them in separate processes while keeping a detailed log for each one of them. Historically, quality control of seismic processing procedures was carried out quite unsystematic. Experts performed validation on a small and often unrepresentative subset of data. This approach does not allow to find all areas with errors and artifacts, and they often stay undiscovered until the very late stages of processing, or even until the interpretation phase starts. Essentially, all the procedures following the faulty one should be done all over again. Together with our processing experts, we have developed quality control criteria for the entire survey area after each processing step. The calculated seismic properties are visualized as maps, which highlight field areas where the procedure has failed. In order to see all the benefits of Seismic Pro and check how it actually works, I would like to show you the ground wave attenuation and how we looked for a way to evaluate models at this task. When conducting seismic surveys, there is always a type of noise called ground roll that's caused by vibrations on the near surface layers of the soil. It's large amplitudes, and if it's not removed, further work with seismic data is impossible. Ground roll is usually removed in a semi-automatic mode. The expert selects parameters for the processing procedure based on several seismic gathers and then applies these to all data. We want to build a model that will perform ground roll attenuation automatically. We will feed the model with seismic traces and it will build new denoised traces. The samples not affected by noise will not be changed by the model. Our dataset consists of seismic gathers before and after ground roll attenuation in SegWi format. Now we build our dataset. In fact, we will not load all the traces into memory at once. We will load only the header of SegWi file, and based on the information from there, we will build an index that stores information about the traces. To see what information is in the index, we'll display several records. we can see that the index is based on the common shot gathers, since the first column contains field record. It aligns traces both from raw and clean data. The index is based on field record in length, shows many common shot gathers there is in a dataset. Let's look at the random pair of seismograms. The amplitude are quite large in this dataset, so I calculated 0.95 quantile of absolute amplitude values and limited the possible range of values for visualization in order to be sharp. I also saved this value as a constant, and it will be needed in the future. Now let's divide the data into train and test sets. Our model will get traces as the input, but the index is built on the basis of field records. We'll select 10 seismograms for training, build a new index based on them, and change this type to index by traces. We can see how many traces there are in the train set. We can also have a look at the first records of new index. Addressing is now long traces, first column. Model architecture. Both input and output traces can be represented as numerical data for the same dimension. For such conditions, segmentation models are suitable, and we will use the well-known UNet model. In addition, our model will have a separate attention branch that will determine the area of ground roll. We'll not make changes to the traces outside the ground roll area. The attenuation branch is a BGG7 model with a final layer that learns the beginning and the end of surface wave. With the help of these two numbers, two sigmoids are built, and their product gives a mask for ground roll area. The final trace is combined from the original one and the trace filtered by the main branch of the model. The original trace is used outside the mask and the reconstructed trace inside it, at the same time as the mask is smooth. The border between the original component and the filtered one is blurred. Here we see the model configuration of batch flow format. Here I only set the hyperparameters. I had to write my own model class to implement this rather complex workflow, but there are plenty built-in classes for standard architectures. Now we define helper functions to represent data in a format required for the model. The learning pipeline will be very simple. Load input data and targets, normalize with 0.95 quantile that I determined earlier, and update model weights. In addition, it contains helper actions for initializing the model and creating a variable that will store the loss values at each step. Now we create a dataset based on the trace index and feed it to the pipeline. Now we can run the training. After training is finished, we can plot loss values for each iteration. And definitely look in the inference. Let's define a small function to test the resulting model. The test pipeline is very similar to the training pipeline. It uses exactly the same actions for loading data and pre-processing, but instead of an action to update the model weights, we call the prediction. The prediction result, initial data, target and mask are displayed on the figure. Let's see the model's output for a seismic gather that was not in the train set. Here I have an input gather, model's output, mask for the ground roll area, and the corresponding target gather. We can see that the model has successfully removed the ground roll from the input gather, and the mask is reasonably good for near offsets. The mask is not very accurate on far offsets. Better results can be obtained by using more training data and further hyperparameter tuning. We have developed a metric to compute model's performance that is called MU. In order to use it, we need to make predictions for the test set. We can now compare the model's predictions and the targets from the test set using metrics mu. We get mu approximately 502, and we'll use this value to compare with the other models. Seismic QB facilitates deep learning research on 3D cubes of seismic data. It contains tools for convenient data loading, preprocessing, and adjusting ML pipelines to use with 3D seismic cubes. Seismic QB provides different preprocessing methods for many types of data, ranging from common image distortions like adding noise, flips, and rotations. They are used to enlarge datasets and make final models more robust in transformations that are used in signal processing and seismology like bandwidth, filtering, and many more. Seismic cubes are fairly large objects with sizes of tens of gigabytes. So our library provides means to load seismic data from SegWi files and precompute cube properties for easier future processing. These operations can take considerable time. So the framework has a method to convert seismic cubes to RTF5 format, which enables near instant inference of cube parameters and is almost 100 times faster at loading actual data. Additional data points can be also loaded, like labeled horizons or subterranean faces or almost 2D surface or 3D body inside the volume. A whole seismic cube is usually too large to fit into GPU memory, so before using an ML model, the data should be split into smaller crops. Seismic QB provides means for that and allows defining various cropping strategies. For example, avoiding generating crops from unlabeled locations. Only the data that needed for a particular crop is read from the disk. After all crops in a cube are processed, they can be assembled using various aggregations into a single cube again. By now, the repository contains ready-to-use models for horizon detection, horizon extension, and faces detection. See the example how the model detects horizons. We have developed an algorithm that allows us to turn a sparse wireframe into a high-precision horizon covering the entire cube area in a few hours. Here you can see each step is automated aside from one single stage where just a few hours of expert data preparations are needed to feed it to the model. Your questions is here for sure. What formats do you support? Working with seismic cubes at any stage of processing. Pre-stack, post-stack, and 2D data. This gives us the ability to conveniently work with any data we are provided with. Not only that, but our custom format of data storage can access data up to 30 times faster than regular SegWi can. Since we don't have enough time to go through the complete pipeline, here's a shortened version. In order to receive a production model, all you gotta do is evaluate input data, construct a grid for experts to work on data labeling, and polish it up with training and end result quality control. Everything handled by algorithms. As the main metric, we compare the distribution of amplitudes in a small 10 to 15 milliseconds interval from the horizon with a set of reference traces. This gives you the means to evaluate both changes in a global horizon pattern and local anomalies in tracking and the seismic data itself. Now we will present the algorithms for horizon detection and fault detection in depth, and you'll see how framework for seismic interpretation actually works. One of the main tasks in interpretation is creating structural model of a survey, and this process heavily relies on so-called seismic horizons. Essentially, they are boundaries between different rock properties and can be clearly seen on seismic cubes. As we said before, for the past 100 years, detecting such surfaces has been done manually, via a tedious process of hand-picking with occasional help from auto-picking algorithms. This takes months to complete and produces a lot of errors. Again, we said before that our idea of applying ML to this task is as follows. An expert can label a small amount of data on a very sparse grid, just a few, maybe like 20 slices, and we can use neural network to interpolate those labels onto the whole spatial range. Let's look at the example in a notebook file. It's fully fledged with whole pipeline of creating a very good horizon from a very low amount of labels. First of all, we import all the stuff from our library, from standard libraries, and etc. Then we load the dataset with one cube and one horizon. And this is a hand-tracked reflection. This is very distinct and it's very clear. Probably it's our easiest horizon of all of them. As we need to evaluate labeled surfaces by humans or by models, we developed a special quality map. Again, the greener, the better. And this horizon is trivial, so the map is very green. We want to train on a very sparse grid, as I said. So we created in this cell 7, and it's just 1, 2, 6 slices of data. So out of all points, we take only 6 slices, and it's very reasonable to think that in a real project, a trained expert can label that amount of slices in a matter of minutes. So let's take a look at the model. It's custom encoder-decoder, which consists of dozen resonant blocks with visual attention models. And it's roughly similar to DeepLab v3 architecture. Our pipeline for training describes that we want to load data, load segmentation masks, apply a number of augmentations, and finally, train a model on all that. Here you can see it takes just 2 minutes and the loss curves show steady convergence. Probably we can train it for a touch longer, but it should do just fine on such an easy horizon. We can use it to predict horizon surface on random crops from our testing dataset. And they look really good. So now is the time to make prediction on whole spatial range. We split the cube into small crops, the same size as we use for model training. Use model prediction horizon on each of them, and then combine them into one array. Then we can extract labeled safe surface from it. And the result looks like this. It covers almost all of the points with the exception of those holes. And the metric tells us that this horizon is very good. As we carved our carcass from a human labeled one, we can compare them directly against one another and see that they're almost identical. The difference in most cases is 1 unit, and in case of such thick reflection like this, that's completely fine. As the horizon detected by this pipeline is not perfect, we developed a post-processing procedures. One of them increases the quality, the other enlarges the labeled surface. They use essentially the same techniques, but create 2 inputs for the convolutional neural network. The result looks as follows. You can see that all the holes that were presented are now repaired, as well as any other flaws. Now we can move on to our fault detection. This notebook includes complete code to provide reproducible research using several GPUs. In our experiment, we want to train multiple models in parallel to find the best one. First of all, we define the config of UNet-like model. Here you can see a lot of parameters, but of all them, let's go to configure very flexible models. Basically, you can use default parameters to construct the baseline model. The whole training process is organized as a short and clear pipeline. Here you can see chain of actions, and each one of them is self-explained. For example, crop, create mask, or additive noise. Note that we don't transform any data in that stage, we only describe training procedure. Then you can see that we define auxiliary functions, which will be executed at some iteration of training process. For example, we will call create dataset method before training and dump model method after. Now you can see in cell 7, we show the following images. Those are examples of labels, and we can see that on 2D slices of seismic cube faults are almost straight lines. Our task is to reconstruct them on the basis of seismic data. In here, we define our domain of research. In our experiment, we will train models on different sizes of 2D and 3D crops from seismic data, and for all possible combinations of cubes that we have. The resulting domain consists of all possible values of paths and crop options. Here we define our reproducible experiment using research class from the batch flow library. It's a sequence of pipelines or callables and scheme of their execution. For example, we add create dataset action, which means that we will call only at the initial iteration of training. And run methods we define by the number of simultaneously trained models on the number of available GPUs. The results of an experiment are stored as a data frame, so it's extremely easy to compute different statistics of training procedures by means of pandas interface. Let's check predictions of one of the resulting models. Here we'll check crops from the cubes not included in a training dataset. As we can see, predictions are accurate enough, as sometimes the model detects faults more correctly than in initial annotation. And finally, we construct predictions for the whole cube. We train models on crops, so firstly we aggregate predictions from separate small crops into this resulting cube. Here we can see predicted faults on a slice from a seismic cube. At first glance, the predictions of the model are pretty good. But the question is, how to construct the metric to measure the quality of prediction, which will take into account specificity of data. It will be the next stage of our study. Petriflow is a library for well-logged data processing. It arranges convenient training for machine learning models and simultaneous data consolidation of various types that describe single well. Also, it provides means for loading various types of well data: well logs, core images in daylight, and ultraviolet light, core logs, inclination, stratum layers, boring intervals, properties of core plugs, lithological description of core samples, and all you want. One important issue about well logs is that different types of data can describe different parts of well. To overcome this, framework provides tools for mathematical splitting all logs of interest into segments of adequate lengths where no data is missing. As well as other ML libraries described above, Petriflow has methods for sampling data, data normalization, and visualization. Here's a sample example of log prediction with attention mechanisms implementation, where you can see that low-quality input data on the left side had served as a major setback for model confidence in its prediction, when on the same well log signal further on, it has stabilized its prediction where data quality became bearable. Well logging is a practice of making a detailed record of the geological formations penetrated by a borehole, usually done via a specific sensor. It's an essential method for geoscientists to acquire more knowledge about the conditions below the surface by using physical properties of rocks. Sometimes, one needs to reconstruct the record of a specific missing log using other recorded ones, and this is the task of log prediction. In our case, it's an acoustic log or DT. Data we use to train a model is preprocessed using Petriflow library. Some logs are kept as is, some are transformed by a logarithm for mathematical reasons. Binary masks are created to indicate missing values. Categorical features are one-hot encoded. We define our model config in a simple dictionary-like way. It's an encoder-decoder neural network with a custom amount of stages, filters, and block layouts. We also set an optimizer loss and GPU device here. Here's the pipeline of actions defined to train our model. It mostly consists of data transforming actions, such as making random crops from data to use them during training, stacking and transposing these crops to feed them in the model, initializing our model with params set earlier in the config. Then we train the defined model by running the described pipeline. Loss reaches plateau, meaning model training process has converged. And here's the pipeline for testing the model. The crops from data are not random but sequential. Actions to feed data in the model are the same. After inference, crops are assembled into complete well log. A sample prediction denormalized due to the nature of data produced by the model. And run inference process. After getting the prediction, we need to evaluate them. To do that, we evaluate R squared for each well. Compare actual DT log with the predicted one. And then plot a histogram for all wells to visualize how good our predictions usually are and how often they're very good or very bad. As you can see, the median R squared value over test dataset is 0.74, which is good. There's also sometimes cases when the model gives bad prediction, but they're really rare and occur mostly on badly recorded data. Metrics values are representative but not very intuitive. Let's look at worst predictions we have. On the first picture, we see a prediction that depicts the actual data pretty good, but it's shifted on a constant value for some reason. This happens probably due to errors in the recording of the acoustic log. If observation would have been recorded by sensor correctly, it will match our prediction perfectly. On the second illustration, we see a prediction that is pretty good in the beginning, but deviates from true value in the right part. Why so? There's a cavern there, meaning the actual recorded values are not representative, and actually no prediction can be done on such intervals. And what about our average predictions? Here they go, randomly picked. Both samples reconstruct the original data pretty good, predicting even high frequency oscillations. Well, that's nice. The model predicts target data pretty good, but the results can still be improved. On one of the future steps to perform, we can take is get better data with less recordings, errors, and more features. Our main topic to deliver to the audience today was open tools for oil and gas data science and its integration in production. We have demonstrated to you our stack for upstream, which requires minimal data sacrifice on your side in order to get real-life application. Of course, the choice is always yours, and we won't stand between you and the ugly world of synthetic data solutions. Who knows, maybe you'll get lucky. But I've only heard back from each presenter at each single conference that it's only an experiment and we will investigate further. The era of experiments is over, my friends. You need to stop relying on third party to make your digital transformation, or whatever you call it, happen. Whatever high chair you're sitting in, you need to get up and start data labeling and put it to work. All the programming parts we've got covered for you, so just take it and jumpstart your industrial leadership. Based on several years of building data science solutions in the oil industry, we came up with an average number that can serve as a low-level estimations on savings. Not to mention that it's impossible to evaluate the overall benefit of early integrated exploration and cost reduction. Many companies ask me how much one model can save. But all I can answer is, do you even know how much you're currently losing? We are well aware that all calculations for human mistakes costs are subjective and extremely underestimated. So we propose that you at least use quality control metrics. Because of its implementation, you gain control right away over the processes that has been scarcely changed in the past years, and pretty soon things will go out of hand completely. Do nothing, and your business will become extinct. Thank you for your time and effort. More information on our toolbox can be found in a dedicated repository. Right there, you can gain knowledge and practice from documentation and tutorials, and don't hesitate to test everything out. Even though I might sound mean and metalhead, we are very friendly, so please contact us.